In this talk, I will present our work on the selection-driven query-focused abstractive document summarization. This work has been done with one of my students, and so why query-focused abstractive summarization? This is for several reasons, just to name a few. It is more practical because usually users and the readers, they have point of interest, they are looking for specific information that are related to queries, and we want to answer those queries using summary. Abstractive summarization is more human-like summarization because usually humans, they just generate abstract, and we want to mimic this way. This is for us more natural way of summarizing document. Even the abstractive summarization may be difficult, but we think that it is still essential. Query-focused summarization, it's not new. It has been defined as a task in the doc 2006. However, using the neural network, it is more recent. In 2016, Cow and all used a neural network for the purpose of the extractive summarization. And all in 2016 they did a similar work. So basically in those work, the summarization task were more considered like classification task. In 2017, Nema and her colleagues proposed a neural model for the abstractive query-focused summarization, and they use for solving this task, they use the sequence-to-sequence model. However, as we know, the sequence-to-sequence model and in general the encode-attend-decode model suffer from the noisy encoding problem when they are dealing with long input sequences. So to solve this problem, we are suggesting to use the selective mechanism. The selective mechanism itself, it's not new. It has been proposed by Lin and his colleague in 2018 for different tasks, different settings, and now here we are using for the purpose of the query-focused summarization task. So let's define the query-focused summarization task. So given that I have a query with a set of query words, I have a passage with a sequence of words. The problem is just to generate a summary, which is just a sequence of token or word. However, the main constraint is that the length of the summary should be much smaller than the length of the passage. So the problem is just an optimization problem in which we try to optimize the probability of this sequence given the previous tokens and the query and the passage. So to solve, one way to solve this optimization problem is just to use the sequence-to-sequence model. So this is what we are doing, and let's see how we are going to represent all this data in the sequence-to-sequence model. So at the bottom layer, we have the embedding layer, which is responsible for converting the character, the word, and the sentences to a machine-readable vector space. Hence, we have the concatenation layer, which is just responsible for combining the three embedding layers, the three embedding sequences, sorry. Then we have the encoding layer, which is just responsible for encoding the input sequences using the bidirectional LSTMs. Then we have the Inception layer. So this, I will leave it, I will come because this is where we are doing the selective mechanism, and I will come back to this in the next slide. Then we have the self-attention layer, which is responsible just for strengthening the learning of the future from the bottom layers. Then we have the gated layer. The gated layer is just basically filtering the output of the passage encoder. All those three layers, we apply them just to the passage, and we don't apply them to the query, because usually the query is short in sequence of tokens, and we are unable to apply those layers. Then we have the attention layer, and the attention layer is just responsible for aligning the input sequence for decoding the output sequence. Then we have the final concatenation state. The attention layer, we will apply it to both the passage and the query, and we will concatenate the two, combine the hidden state of the final hidden state of both the query and the passage. Then we have the decoder side. So the decoder side, we are having just the embedding layer, in which we convert just the summary word into vector space. Then we start the decoding. The decoding is just for the output sequence. Then we have the output layer, and the output layer is just doing the prediction for the summary words. Now the inception layer basically is responsible for the selection mechanism, and it is just responsible for learning the local and the global features. So basically we have five inception modules, that are chained together, each module having a varied size, and between each module we have just five residual functions. So for those, I'm not going to go for those details. So basically the residual function just insert, they are just in order just to they are just shortcut for the back propagation when it is difficult to compute the gradient. So all the details for this, I'm going to skip them. Now on the top we have just the concatenation layer, which is just a linear function, and that the final output that will be going to the attention layer. Basically, so this model, yeah, so we experiment with this model. So basically we used the Debatepedia dataset that was provided by Nema and her colleagues. So basically they are just parliamentarian debate, which we have the query, the passage, and the summary. To run our experiment, we use just a machine that has an NVIDIA Titan X GPU card with 12 gig of RAM, and we used several metrics for the evaluation. So we use ROUGE, Meteor, ESC, GMS, and the copy rate. And we compared our model against the diversity model, which is the NEMA and all model. So as we can see, in all the three ROUGE scores, we can beat them. And however, we couldn't compare our model using the other metrics, because this we take it just from the original paper, and this metric, when we try to reproduce the experiment, we were unable, and even when we asked the author, they were unable to provide us with the data. So in short, in this paper we have presented a selective mechanism which can handle the long input sequences in the encode-attend-decoder. As future work for this work, we are lacking data sets, so probably we have to come up with some other data sets, and also some other future work. We can use more powerful architectures such as the transformer and the BERT architecture. Thank you.